Aloha, my favorite class. Hello. Let's keep going with our 1-4 additions. It's so exciting. I can't wait till we get to our rings. It's going to be fun. So our last video, we kind of introduced the idea of a 1-4 addition, and we used as our nucleophiles, we used 2 nucleophiles. We used cyanide and we used ammonia. But this could be any kind of amine. This could be some sort of secondary amine. This could be anything but a tertiary amine. We could have also in the form of the amine salt. So we could have any of those. And then we've got 2 more I'd like to tackle in this video, and that's going to be our Gillman. Oh, I ran out of room. Darn it. Let me erase here. That's going to be our Gillman. And then finally our enols or enolates. Awesome. All right, our Gillman, I actually posted our organometallics series first, so you could take a look at the Gillman. You may or may not have tackled the Gillman in Organic 1. Let's do a little review. There's more detail in that organometallics video. Our Gillman reagents start with alkyl halides. So you can take any kind of alkyl halide. We know how to convert an alcohol to an alkyl halide. We did that in Unit 2. And then what we're going to do is some transition metal chemistry. We're going to do some organometallics. And our first step is to do a lithium exchange. And that second step is to add copper iodide. And what you end up making, it looks a little crazy, but let's simplify it. So you end up adding not just 1, but 2 of your alkyl halides to your copper. And you're going to react right here. Okay, it turns out that carbon is going to have a partial negative, and it's going to act like our nucleophile. And then our copper will, of course, have a positive charge on it. And the funny thing is that even though there's a 2 here, one of them is called a dummy ligand. So with our cuprates, with those Gillman reagents, only one of this R carbon unit, only one of those is going to react. So even though the reagent looks a little sassy for the 2 there, you're actually only going to react one of them. Let me show you what I mean. So what I like to do is sort of write a Gillman like a Grignard. It's probably not completely accurate. You know, when you think of a Gillman, it's one big complex with copper and a lot of stuff in there. But what it really is going to look like in our mechanism is a negative right there where this bromine was. So you're inserting right into that bond and you're making that carbon a negative. So I kind of picture it just like we did with our Grignard. That's a bigger complex with a metal, but we can picture it as that negative and a nucleophile in our mechanism. So it turns out that if you were to add a Grignard to these compounds, your Grignard will add 1, 2. If you add a Gillman, so we have a different metal, we went from magnesium in a Grignard to copper in a Gillman. Now our Gillman is going to add here, 1,4 addition. Isn't that phenomenal? You change your metal and you have completely different selectivity. So take a screenshot of this real quick. I'm going to erase and then draw the mechanism for that. So once you've made your Gillman reagent, we're going to use it just like a Grignard. It just looks a little bit sassier, but we're going to react it very similar. So let's take our substrate up here from our aldol, and let's go ahead and add a Gillman to that. Okay, so let me redraw this one. And then let's go ahead and just kind of pick a Gillman reagent. I'm just going to maybe do an isopropyl. It's a little bit sassier to draw. That way you can kind of keep track of it. What I like to do is just remind myself, look, this is the carbon that's going to have the negative. That's the copper attached to the carbon. That bond is the one that's going to transfer. Whoa, what just happened there? And that's where we're going to react. So I'm going to picture this, let's use 1980s air quotes, as a nucleophile right on that carbon, right there. And that's the carbon that was attached to copper. Okay, so let's use it. Let's kind of draw it just like we would draw our Grignard, only the difference is those electrons now are going here. And in our 1,4 addition, remember the only reason these work is these electrons have a place to go. They can go right here, and that double bond can go right up there. All right, let's draw the product of that. So I'm going to start with my little mustache there. Our electrons ended up here. Here's our new double bond, and we just added that Gillman right there. Okay, and then the same thing with the Gillman that we had in our other reactions. This Gillman would be step number 1. Step number 2 would be some sort of acid quench, kind of like what we did with our Grignard back in Unit 2. So we would have some sort of acid quench in there, and we would quench that enolate. So what does our final product look like? Well, we reform this double bond. We form a bond to hydrogen here, and then we just added whatever was on our Gillman reagent. Okay. Aha! So we just did a full substitution, 1, 2, 3. And we can literally add any kind of alkyl group here. Gillman reagents work really well with alkanes, with alkyl halides. They work fairly well with vinyl or alkene or some kind of double bond. They don't work well with an alkyne. Alkynes will actually stick to your copper way too much and they won't transfer, and they're typically something called a dummy ligand. They just don't leave the copper, so the reaction doesn't quite work. So let's put a little sparkle pen around this. That's awesome. Let's turn right around and do this again. Let's do another Gillman. Let's put our ring substrate out there for 1,4 addition, and let's draw something a little bit crazy with our Gillman, just so we can practice which carbons end up where. So take a screenshot of this. I am going to erase, so we're going to do it again. Can you just feel your synthesis getting fun? I mean, we're only 2 steps in on an aldol, and we're making some pretty good substitutions. Okay, let's take our ring substrate, one of our favorites. And let's take another ring, and let's make that our Gillman. Remember, any alkyl halide, how do you make that into your Gillman? Number 1, lithium halogen exchange. Number 2, you're going to add some copper iodide. So that is now going to look like copper where your bromine was, but remember, you add 2 of them. All right, let's mix that. Let's take that conjugated ketone, and then how do we view this? Which carbon is going to be the negative in our Gillman? Right there, the one attached to copper. So if I want to draw this in a mechanism, I'm going to put a negative right there. I'm going to picture that as my reagent, and now that is going to add 1,4. Okay, let's draw the product there. All right, our electrons now end up all the way up here. We've got a minus. Oh, that looks terrible. Let's do that again. Our double bond is here, and we just added our ring right there. And then now we've got any kind of acid quench in there is number 3. so let's quench our enolate. And let's see what our product is. Okay, like that. We quenched there and we added our Gillman there. What a great way to substitute in all kinds of ways on our cyclohexanone. So the Gillman is a pretty good way to start adding stuff. Just remember, where is it going to end up? 1, 2, 3. And that number 3 spot, you can add any kind of alkane or alkane chain. It's pretty fun. All right, let's take a minute and I'm going to scroll down just a little bit. Let's do the last one. The last one after a Gillman is to use another enolate. Okay, just wait for it. Remember, we've got a nice little tautomerization happening here. We've got enols. Remember, from our aldol, these can be good electrophiles, and our enols are good nucleophiles. So it turns out enols or enolates, we can also make that happen. We don't have to wait for that 1%. We can make that 100% with the base. That enolate turns out is a good nucleophile for 1,4 additions. All right, so let's scroll down just a little bit and let's try to draw one of those. This is going to be so much fun. I can't wait. All right, let's take our same substrate, our nice kind of plain Jane, our most basic aldol. Let's take that. And then how would we make that happen? Well, let's just add in our enolate and draw our mechanism, and then we'll turn around and write it like you would have it in synthesis. So let's add one of our enolates as our nucleophile. And let's see what we get. All right, so we're going to treat this 1, 2, that's our nucleophile. The only thing that's different is that this isn't our number 3 anymore. This is, okay? We're doing the same as an aldol, except when you already have that conjugated system, your nucleophile reacts here, not here. So let's keep going on our mechanism. Where do these electrons go? They are all connected all the way up to that oxygen. So what do we get when we combine those two? Let's draw our little mustache from our aldol. Our electrons end up right up there, okay? And then we ended up with a double bond here, and we just formed a bond there with that enolate. Okay, remember here was our 1, 2. We added into there. And then now let's use some kind of acid, whether that's more of our enolate or our enol, excuse me, or we have a quench. We have a nice acidic quench. Let's add that. And then let's see what we get. All right, let's color code a little bit. Okay, we just quenched there, we just added there. We've got our hydrogen here, and we added in our enol, or our enolate there. Oh my gosh, that's so awesome. Why am I so excited right now? Does anybody recognize where we're headed? I'm sorry, but if there was ever a sparkle pen moment, this is it. Holy crap. Look at that. That deserves some major sparkle. Why am I so excited? Okay, how did we get to this? One step, aldol. How did we then get to this? One step, 1,4 addition. And now you know where I'm headed. Are we done with this substrate? Or can we move on from this substrate and do even more? In fact, you can do even more. This is so exciting. We're getting into a named reaction here. And I have to just we're about to have the most fun ever in Organic 2. Unit 4 is my favorite for things like that. Does anybody know? Just pause for a second. It's like a cliffhanger. Why am I so excited by this setup in this system? I want to number one more time, and then we're hitting a famous reaction here. Okay, let's number. Where are my oxygens? 1, 2, 3, 4, 5. Aha. This is going to be so much fun. I want you to keep in mind this is a new spacing. When those oxygens are 1, 5, we are headed to rings. Oh my gosh, this is going to be so exciting. So if you can believe this type of reaction, the specific substrates were with some esters, but now 150 years later, the general term of a Michael reaction is used. Anytime you do a 1,4 addition with an enolate, it's often given the term Michael addition. Michael additions actually started, whoa, what happened? Michael additions actually started in the 1800s. Can you believe that? I mean, no idea what an electron was, and he is reacting enolates and 1,4 additions. I mean, it's ridiculous. This reaction has been around for so long. So I've included some fun links for you here. There's a nice Wikipedia link. This little paragraph comes from Wikipedia. It has exactly what we were just saying. Hang on a second. Why this has been around for 150 years? It is still being used. There are many iterations of the Michael reaction. It depends what your source of your enol or enolate is. There's lots of Michael additions. They are still used, and they're still used because of this 1,5 dioxygen spacing. They make phenomenal partners for all kinds of chemistry. And we're about to make some rings with them. So in our Michael addition, this is so exciting. Let's just spell it out again from the beginning. And let's look at how simple yet how complex it is all at the same time. Let's start with basic acetone. We learned in our last unit, cook this up together, mix an acetone with an acetone and a little bit of heat. And in one aldol step, we could make this. Okay, wonderful. Here's our 1, 2, 3 spacing, and we can dehydrate that, lose water. We've got that double bond. Well, now we're learning, well, sweet Jesus, that's not where you stop. That's just where you start. After that aldol, we have a nice conjugated system. This second step is all about unit 4. What can we add into this second step? Our Michael reaction is quite specific to enols or enolates, but you can have a variety of enols and enolates. As we work our way through this section in our Claisen section, we're going to start with a general enol or enolate like we've seen from a ketone or an aldehyde. They can also be from a diketo compound, and then we will get big enough to see where these could also be esters. So the source of enols and enolates are actually going to grow in our Michael reaction, but let's start with the most basic and just see what that process is. So that's the one that we just drew. It turns out, let's take a second on why we even care about these and why those are so common. In fact, I think the original Michael reaction had one of these with some esters. So if you have just acetone, remember that equilibrium, that tautomerization into that enol, you have mostly this one, somewhere between 99 and 97% is actually the ketone. Well, the second you have two of them in your substrate, whether those are ketones, aldehydes, or esters, so I'm going to put an R here, you're now going to favor, in fact, you'll have close to 70%, depending on your substrate, the enol form without even needing base. So that's what makes these so different. Now you might be upwards of 50 to 70% of the actual enol. So that whole dynamic is changed when you have two of them. That's why you see them all over the place for this chemistry. Okay, we just did the mechanism for this top one, for that nice generic. So what happens if you take acetone, you heat it up, you do an aldol, and then you add acetone again as your enol, you make a substrate like this. Isn't this awesome? This is your 1,2 from your acetone, and then you add it in here to your conjugate addition. And if you keep numbering, you notice your oxygens are 5 apart. So this is where we begin. This is so much fun, because now let's do some counting and let's do some drawing. And this is exactly what's on your Unit 3 test right now. Can we form a ring? Can you now do an aldol with this and itself? Absolutely. This is on your take-home test right now. Let's do some counting and some drawing. So we kept it nice here because it's an aldehyde. So let me draw some of our options for our enols, and let's do some counting and see what we can make. All right, so if we count this one, 1, 2, 3 on an aldol, then what size ring are we about to have? We're about to form that bond between 2 and 3. So that's going to give us 1, 2, 3, 4-membered ring. That is not going to happen, right? 4-membered rings, they're not going to happen. So let's check another one. What if we take this one and let's do some counting there. 1, 2, 3. So where do we form those bonds? Between 2 and 3. So let's count our ring size then. 1, 2, 3, 4. Nope, 4-membered ring, not going to happen. All right, let's check the last one then. Let's draw this one. Let's take and let's draw this side enol. All right, let's count those. 1, 2, 3. All right, where do we form our bond? Always between 2 and 3 in our aldol. Oh, wait a second. This looks promising. How big is this ring? 1, 2, 3, 4, 5, 6. There you go. Aha. So now we can make a ring. Let's go ahead and draw it. You know what my super secret is. I like to draw the ring first. Let's draw the 6-membered ring. You already know you're about to make a 6-membered ring. So now let's number. Okay, where are we making that 6-membered ring? We are going from 1, 2, 3. We're forming that bond between 2 and 3. So I'm going to draw that. We're forming that bond. What is happening to number 1? We are reforming the ketone part. What happens on number 3? That is your aldol part. You end up making the alcohol. And then don't we also have some extra stuff hanging off? We do. We've got a methyl group right there. Where should we put that? How about right there? Okay. All right, this is so fun. I did this pretty fast because we just did this in class in aldol before spring break. So normally I would draw that much slower, but we've already done these in class. All right, so let's take this then. You know, we're not done. A little bit of heat. And now what did we just make? That. Okay, let's just review for a second. This is so powerful. This is why the aldol, the aldol, the Michael, all of these reactions are used today. They've been around for 150 years. Look at this. We started with one step. This is our first step. We just did an aldol, dirt cheap and easy. We went super complicated from here to here, and all we did was heat that up and get that going. You could also just add base to make that even better. All right, second step, we did a nice 1,4 addition. That 1,4 addition, all we had to do was add a little base or heat to that 1,4 addition, and we went all the way to that ring structure. I mean, in 3 steps, we went from acetone all the way down to this cyclohexanone. If that doesn't scream test question somewhere, I don't know what does. So you guys, that needs to be on your cheat sheet, and we need to practice those. And then just wait for it. We're not even done yet. This is a 3-step, right? And then, do you know where I'm headed? Obviously, sparkle pen on this one. Take a look at that substrate. Did we not set ourselves up for even more chemistry? Doesn't that substrate look an awful lot like something that we can, I just recognized that there is a carbon there and there shouldn't be. Okay, so doesn't that look like something we can do an additional 1,4 addition? Oh, yeah, that's right, I went there. That is exactly what you can do. This reaction has also been around since about the 1930s. This is a named reaction. Now we're going to do a couple of these. This is a named reaction called a Robinson annulation. And that is where Robinson made that connection as well. Wait a second. If I can literally start with a ketone and end up all the way making a ring with a Michael addition, why can't I turn right around and do it again? And now I'm going to make a fused ring system. So what if we imagine a 1,4 addition here? Now we already know we can make that using aldol chemistry. Okay. And then what if we use a ketone? Now we just saw that we can make this with a Michael and a 1,4 addition. Well, our 1,4 addition is our Michael. And then even backwards, one more step from an aldol. Okay, we can make both of these substrates using aldol chemistry in 1,4 addition. So what happens then if you mix them? Let's put them together. So let's write this out like we would actually write it in lab. And then we better take some time, maybe in our next video, to write out some of these. So what happens then if we mix it? Let's take our cyclohexanone right there, and let's treat it with base. So let's draw that first step. Let's draw that as a mechanism. Let's draw that first step. Okay, we know we're going to deprotonate. That's why we've got our base in there. And we are going to form that enolate, excuse me. Okay. All right, so there is our nucleophile. And as soon as we add in now number 2, we are going to add in, I'm just going to write it this way. I'm not going to write it that way. That looks ugly. Okay, I'm going to write it like that. Let's add that in. All right, how can we react this? This is a 1,4 addition. Here is your enolate. Here is your 1,4 addition. What do we get from that? Okay, well, let's flip that around. We just added, let's form a bond here. Okay, we just reformed this one. We just reached out here. And we just went all the way. Okay, let me make sure my spacing's right there. We just went 2, 3. Our electrons just went all the way to there, and then all the way up here, like that. All right, let's go ahead and quench that with some kind of acid step. That's our number 3. So let's go ahead and quench that enolate right there. And then let's draw that nice. What is that really going to look like? Okay, we just formed a bond there. We just quenched there. We reformed our bond there. Okay. Oh my gosh, that is sparkle pen again, if I've ever seen one. So do you think we're done here? No, not at all. Because now, can we form another ring? Absolutely. We have options here, don't we, of some enols, and we have some options there. So we better scroll down a little bit. Robinson is not done. Let's call this an intermediate because we are not done. Especially if you've got some kind of reactive conditions, we are going to cyclize that whole thing again. So I am going to scroll down and I'm going to write those rings in all kinds of ways. We already know this process. Isn't this the test we just took? What do we do to this thing? We start writing it. What are our options? Okay, we can have an enol on this side. And holy cow, let's just count our spacing. Those oxygens are 5 apart again. That's that key spacing. All right, we can have an enol there. Let's number 1, 2, 3 for our aldol numbering. What size ring is that going to be? 1, 2, 3, 4. Probably not going to happen. Let's draw another one. Okay, let's do our enol on the other side then. Okay, and we've got 1, 2, 3. Let's count now. 1, 2, 3, 4, 5, 6. We have a winner. This one's going to give us a 6-membered ring. I love it. Okay, let's keep going. Let's see if we've got other options. Can't we have an enol on the other side? Absolutely. Let's draw that one. Okay, 1, 2, 3. I love it. All right, how many in this ring? 1, 2, 3, 4. Probably not going to happen. All right, let's draw the last one then. All right, what's your gut tell you? How many are going to be in this one? Here's our 1, 2, 3. How many carbons are going to be in that ring? 1, 2, 3, 4, 5, 6. There we go. We have another winner. We've got a 6-membered ring. Okay. So let's draw that. What in the world would one of those look like? Well, we're about to form a bond between 2 and all the way up to 3. Let's draw it. Okay, what do we leave behind on number 3? Oh my God, that's ugly. Don't draw that. Let's color code for a second. Which bond did we just form? We just formed this one. In fact, this would be our 1, 2, 3. So where do we reform our ketone? Right here. Okay, isn't that awesome? And then wait for it, you're not done. What happens when you add just a little bit of heat to that? You are going to make a nice fused bicyclic ring right there. Could you add more to that? Yes, but let's stop right here. Let's pause for a second. Now let's look at how far we have just come. This was one step. Robinson annulation is one step all the way back from these two substrates. And here's what's phenomenal synthesis-wise. You can make that in one step, and you can make that 2 to 3 steps, depending how you heat and how you add that, and you can make that. This entire synthesis to make this fused ring system, you could do in 4 steps. That is phenomenal. This is why this type of chemistry has been around forever, That's why this type of chemistry is so productive, and it is still used today in all kinds of iterations. It's really, really awesome chemistry. So what we just did was introduce some pretty crazy concepts, but what's beautiful is you've already seen half of it. We've done aldol in our sleep. What we're doing is taking aldol and putting it on steroids and making rings and going crazy with our aldol. So try some of these, digest this a little bit, and then our next round of videos with these, we will just apply. So I'm going to stop with this one right now that we've introduced the Michael and we've introduced the Robinson annulation. I have homework on both of these posted. I want you to try it, and then we're going to do some of that homework together.